In this lesson, we are going to find confidence intervals for the difference of two means from two independent samples. So in this case, we have two populations or groups from which independent samples are available. Contrast this with a paired case where the first sample and second sample are not independent because you have two measurements for the same person. We're interested in comparing the means for these two groups of populations. One example might be the mean cold length for a drug group versus a placebo group. Another example might be we want to compare the average height of Dutch people to the average height of Japanese people and see if there's any difference in the average heights of these groups. So the first things we have to find are the means for each group, which would be x1 bar and x2 bar, and compute the difference, x1 bar minus x2 bar. Your textbook often just tells you to put the larger number first. It's pretty commonly the case, but nothing says that it has to be that way. The standard error is found using the following formula back from chapter 9, where standard error of x1 bar minus x2 bar is equal to the square root of the first sample standard deviation squared over n1 plus the second sample standard deviation squared over n2. And then the last thing we're going to need is the degrees of freedom, which will let us find our multiplier. And we use an approximation of t star. And the only thing that's a little bit different here is how do you find your degrees of freedom? Well, the n that you choose to use for the degrees of freedom is the smaller of the two samples. So the conditions that guarantee that this procedure is going to be valid, the first condition, much like before, is that the populations of measurements are both bell-shaped and random samples are measured. The observed data shouldn't show any extreme skewness and there shouldn't be any outliers. And in that case, any size is okay. And condition 2 is that you measure a large random sample. And in this case, it's best that n is bigger than or equal to 30, but bigger is generally speaking better. So suppose that you were given a 95% confidence interval for the difference between two population means. What could you conclude about the population means if the interval does not cover 0? Well, if the interval does not cover 0, this means mu1 minus mu2 probably isn't equal to 0, or 0 is not a plausible value, or we could say plausible or likely value. So if the difference in the two means is not 0, this means that mu1 not equal to mu2. In other words, the two means are different. And if the interval does cover 0, well, then you can't draw any conclusion. It may be the case that mu1 minus mu2, the difference in means is 0, or may not. But the difference in part B here is that you can't rule out mu1 minus mu2 equals 0. It's still possible. All right, let's find a confidence interval for the difference in two population means. So for a sample of 36 men, the mean head circumference is 57.5 centimeters with a standard deviation of 2.4. And for a sample of 36 women, the mean head circumference is 55.3 with a sample standard deviation of 1.8. So find the value of the difference between the sample means for men and women, and we're going to use men minus women. So our sample statistic is x1 bar minus x2 bar, and x1 bar is the average head circumference for men, which is 57.5, minus the average head circumference for women, which is 55.3, and that difference comes out to be 2.2. Find the standard error of the difference between the sample means in this context. Well, the standard error for x1 bar minus x2 bar is equal to the square root of s1 squared over n1 plus s2 squared over n2. Okay, S1, sample standard deviation for the men, well, that standard deviation was 2.4 over N1, which was 36, plus sample standard deviation for women's head circumference was 1.8. And make sure that your calculator will give you this as well. I got this as about 0.5. Now, find an approximate 95% confidence interval for the difference between population mean head circumferences for men versus women. So the first things, we have the standard error, we have the x1 bar minus x2 bar, we need the t star. So we take n to be the smaller of the two. Well, both sample sizes are 36, so our n will be 36. So the degrees of freedom is 35. And I'm going to take t star equal to 2.03, because 35 isn't on my table, but I averaged the t star for df equals 30 and 40. That's how I found that. Now the format of this confidence interval is just a teensy bit different, but not much, because you're talking about a confidence interval for the difference. Well, we're taking x1 bar minus x2 bar plus or minus our t star times the standard error of x1 bar minus x2 bar. It's almost the exact same as the previous lesson, except for the only difference is that you have x1 minus x2 bar instead of a singular x bar or a singular d bar. So we have 2.2 plus or minus 2.03 times 0.5, which comes out to be 1.19 to 3.22. And let's interpret this. So with 95% confidence, men have a head circumference between 1.19 and 3.22 centimeters greater than women on average. Now, when your sample sizes start to go larger than 30, you can see from your table that that t-star multiplier gets pretty close to the z-star multiplier. And so it's really okay that once the sample sizes are at least 30, you can use 2 for the multiplier when finding your 95% confidence interval. And confirm this using your t-table. A sample of n equals 30 corresponds to a degrees of freedom of 29. And in this case, t star is going to be about equal to 2.04. So the idea is that as your sample size or your degrees of freedom increases, that multiplier gets closer and closer to the 2 you know from using the multipliers for proportions. Probably best to use the most specific ones, just so I know that you're using the right table, but 2 might be good enough past a certain point. So here we're going to find a confidence interval for a study that's comparing weight loss between diets and exercise. So we have 42 men who are put on a diet, and 47 were assigned exercise. The men who were on the diet lost an average of 7.2 kilograms. That's actually a fair amount of weight. Multiply it by 2.2 to get how many pounds. And a standard deviation of 3.7 kilograms. The men who exercised lost an average of 4.0 kilograms with a standard deviation of 3.9. So compute the difference in means. Let's use diet minus exercise. So x1 bar minus x2 bar is a 7.2 minus 4.0, which is 3.2. So the difference in these two averages is 3.2 kilograms. Find the standard error. Well, the standard error of x1 bar minus x2 bar is equal to the square root of s1 squared over n1 plus s2 squared over n2. Okay, s1 is 3.7 squared over n1, which was 42. And then the sample standard deviation for the exercise was 3.9 squared over that sample size was 47. You should verify this yourself, but you get approximately 0.806. So find an approximate 95% confidence interval for the difference in these means. So remember, the format of that confidence interval is x1 bar minus x2 bar plus or minus t star times the standard error of x1 bar minus x2 bar. So we need to figure out what we're going to use for t star. Well, we take our degrees of freedom to be the smaller of the n's minus 1. So our degrees of freedom is 42 minus 1, which is 41. On our table, the closest thing we have to that is df equals 40. But since 40 is bigger than 30, we know that this t star is going to be pretty darn close to 2. I think it ends up being 2.02 exactly, but just for making the ease of computations better, let's just use 2. So we have x1 bar minus x2 bar is 3.2 plus or minus 2 times the standard error of 0.806, which comes out to be 1.59 to 4.81. And let's give a quick interpretation of that and sort of an explanation of which program was better. So men who were placed on a blank did better. Well, it looks like the diet group lost more weight. So men who were placed on a diet lose between 1.59 and 4.81 kilograms more than those on exercise. And this is with 95% confidence. So it appears that in this case, diet outperforms exercise. And one way that you can say that diet is definitely doing better is that this interval is entirely positive, meaning above 0, which meaning that this x1 has to be bigger than that x2. Now, sometimes it can be quite helpful to, because you have taken measurements from 2 different groups, it'd be nice to put your groups together into thinking about them sort of as one group. And the way that you can do that is you can make an equal variance assumption and then use something called the pooled standard error. So it may occasionally be reasonable to assume that the populations have equal standard deviations. And since the term variance describes the square of the standard deviation, remember that back when we first learned about this, S was equal to the standard deviation, S squared is this thing called the variance. And this assumes assuming you have two equal standard deviations implies that the variances will also be equal. And so you use this pooling, so use if sample standard deviation 1 is approximately equal to sample standard deviation 2. And how close is close enough is a little bit up to you, but in general, if they're close together, or I state somewhere that there's approximately equal spread, then it's safe to pool these things together. So the formula that puts them together is given right here. And what this does is it kind of does a little bit of a weighted average where it puts those standard deviations together and makes a new standard deviation. And then the first thing you do when you have this is you find SP using that thing up there. And then the next thing you do is you find the pooled standard error. And how you do that, SE of x1 bar minus x2 bar, in this case is equal to the square root of SP squared over N1 plus SP squared over N2. Versus the unpooled, which was like this. S1 squared over N1 plus S2 squared over N2. And the way to remember which is which, I mean, just think the pooled puts them into one pool and puts them together. So that's the best way to think about it. And as long as your sample standard deviations are pretty similar, it's possible to put them together in this fashion. And one nice thing about this is it lets you use bigger degrees of freedom, which decreases your multiplier. So here is the format for that pooled confidence interval. So you see how we have this thing is the pooled standard error. And the real difference, other than that, comes from finding the multiplier. So the multiplier is found using a t distribution, but now your degrees of freedom is bigger. You add those sample sizes together and taking away 2. It's kind of like this comes from n1 minus 1 plus n2 minus 1, and that's one reason you can see where that minus 2 comes from. But the advantage here is that larger degrees of freedom, so larger df implies smaller t star, which implies a narrower interval. All right, well, let's revisit this example about taking zinc to fight the common cold. So remember, there were 25 people taking the zinc, and the mean overall duration of their symptoms was 4.5 days, with a standard deviation of 1.6. For the 23 in the placebo group, the mean overall duration was 8.1, with a standard deviation of 1.8. So first, let's find a 95% confidence interval for the differences, and let's use placebo minus zinc and the unpooled procedure. In the previous lesson, we did this example by finding 2 intervals. This time we're going to just find 1 for the difference. So first find the mean, x1 bar minus x2 bar. So placebo minus zinc. Well, the placebo's average cold length was 8.1 days, minus zinc's, which is 4.5, works out to be 3.6. Next, find the standard error. And because we're using the unpooled procedure, the formula for this is S1 squared over N1 plus S2 squared over N2, square root of 1.6 squared over 25 plus 1.8 squared over 23, which works out to be approximately 0.49. Next, we need the multiplier. And we use the smaller number to get, or smaller n, to get the degrees of freedom. So smaller n is n2, which is 23. So that tells us our degrees of freedom is 22. So the t star we have to use here is 2.07. And the 95% CI is x1 bar minus x2 bar, plus or minus that t star, times the standard error of x1 bar minus x2 bar. So 3.6 plus or minus 2.07 times 0.49, which works out to be 2.59 to 4.61. And what this tells us is that with 95% confidence, the average length of cold, or duration, whatever you want to say, is 2.59 to 4.61 days longer on the placebo versus the zinc. And now let's look and see what doing the pooled procedure does to our interval. So repeat part A using the pooled procedure. So certain things are the same. So the first thing that's the same is that the mean, which is still x1 bar minus x2 bar, that's still 3.6. The difference is in finding the standard error. So second step part A is to get SP, so the pooled sample standard deviation. And one reason it's reasonable to use the pooled procedure here is the standard deviations are awfully similar, 1.6 versus 1.8. Now what we're doing here is kind of a weighted average. This average will actually end up being 1.6 plus 1.8 over 2, but that's because these sample sizes are awfully similar. And if that were not the case, then it would not be such an easy average. So the formula for SP is root n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over n1 plus n2 minus 2. So plugging everything in, n1 is first sample size, which is 25. That standard deviation was 1.6. N2 was 23. That sample standard deviation was 1.8 over 25 plus 23 minus 2. And to verify that you can get this, you get approximately 1.6986, which, just to make stuff easier, I'm going to round to 1.7. Okay, now you're not quite done yet. This is just your SP. So step B is to get the pooled standard error, which is SP squared over N1 plus SP squared over N2. So there we have 1.7 squared over 25 plus 1.7 squared over 23, which comes out to be approximately, once again, 0.49. That might be more different if I'd rounded differently, but it is pretty close to what we got in the previous example. Okay, next we need to find our t star. So we use, for degrees of freedom, it's n1 plus n2 minus 2. So 25 minus, or plus 23 minus 2 comes out to be 46. and looking at a table and perhaps averaging the t-stars for 50 and 40, we end up with a t-star awfully close to 2. I used 2.01 in my calculations. So our 95% CI is 3.6 plus or minus 0.49 times 2.01, which is 2.62 to 4.58. And this interval is a little bit narrower than the one we got in part A. So compare the unpooled and pooled results and discuss which procedure is more appropriate. So the pooled procedure is more appropriate when the sample standard deviations are similar. And so since S1 and S2 are close together, the better procedure in this case is the pooled procedure. So the last example that we're going to go over for section 11.4 is something for which I'd like to just show you how to use Excel for some stuff. Just tell you what the commands are. I'd like you to try to do it yourself in something like Excel, or if you don't have Excel, something like OpenOffice that's free. So here we have data for 20 individuals, and we have their resting pulse rates and whether or not they exercise regularly. And we want to compare the exercise regularly group to the don't exercise regularly group. And the only thing I want to focus on in this question is just finding the mean and standard deviation for both groups. So first you have to separate them into groups. So we have the yes group, so we'll let x1 bar equal the mean resting PUL pulse of the yes, and we'll let x2 equal the mean resting pulse of the no groups. So one way to put this into Excel is to take all of the, say, yeses, which would be these two, these two, these two, these two, and those 4. Looks like there are 12 of them. 2, 4, 6, 8, plus 4 is 12. So x1 bar obviously is going to be adding these up and averaging them. So like 62 plus 72 plus 60, blah, 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 until you get up to 64. And if you divide then by 12, the average pulse rate for this group you get is 65.3. To put this into Excel, if you'd like to, x1 bar could be found using, type in an equal sign, and then type in average. And you can either put these numbers in a column and highlight the whole column, or you can put them in a list. 62, 72, put them all in. Last number is 64, and you get 65.3. Similarly, x2 bar, you type in average, and you put in 72, 84, 66, etc. up to the last one we have there is 60. That should come out to be 72. Make sure that you can make Excel or some technology do that for you. Because the really useful thing to use technology for here is for the standard deviation. Because remember that to find the standard deviation, S, this is equal to square root of a sum, your x value minus your mean squared divided by n minus 1. Which means for the first group, you'd have to do, say, 62 minus 65.3 squared plus 72 minus 65.3 squared. For all of those circled values, it's just going to get very tedious. So the best way to do it is to use Excel. So S1, the sample standard deviation for sample 1, is equal to STDev for standard deviation. And then if you have your numbers already put in a column, or you can put them in a list, 62, 72, etc., put them all in. Last number is 64. Make sure you don't miss anybody. And this should come out to be 7.49. Make sure you can make Excel do that for you. And similarly, S2, STDev, you put in 72, 84, etc. The last number you put in is 60, and that comes out to be 9.13. So make sure that you can do this on your own using Excel. And the final thing I want to talk about was an example of something that I read a few years ago that made me pretty interested in statistics. So this is an abstract for a Stanford study, like for real, done by Stanford, that compared weight loss among 4 different diets. I found this abstract at this website, which you can also go and read it yourself. I first read about this study when I was reading a book about diet and health. So here is the summary of what the abstract says. So the context is that popular diets, particularly those low in carbohydrates, have challenged current recommendations advising a low-fat, high-carb diet for weight loss. So potential benefits and risks have not been tested adequately. So back in the 80s especially, fat was bad for you, don't eat fat ever, and you were supposed to eat a low-fat diet to lose weight. And this study was trying to address, well, is that actually the right advice to give? So the objective of this study was to compare 4 weight loss diets that represented a spectrum of low to high carbohydrate intake for effects on weight loss, and then related metabolic variables. And what those things are things like blood pressure, cholesterol, stuff like that. All right, here's where they describe the design of the experiment. So 12-month randomized trial. So these people were put on a 12-month diet, conducted in the U.S. from February 2003 to October 2005 among 311 free living overweight or obese, BMIs between 27 and 40, non-diabetic premenopausal women. The intervention, participants were randomly assigned to follow the Atkins diet, 77 on that one, the Zone diet, 79, the Learn diet, 79, and the Ornish diet, which was 76 people. And these people received weekly instruction for 2 months, and then an additional 10-month follow-up. So one interesting thing about this study is people were sort of left on their own because they had weekly supervision for 2 months, but then there's just a 10-month follow-up. And notice the whole free living thing also would test and see how easily can these people follow their diet when they're living in the real world, so to speak. Also note that the sample sizes are all bigger than 30, which is a good sign. And so here is the summary of their results. So weight loss was greater for women in the Atkins diet group compared with the other diet groups at 12 months. And the mean 12-month weight loss was significantly different between the Atkins and the Zone diets. And this had a probability of less than 0.05. So here are the mean 12-month weight loss intervals. So the mean weight loss on the Atkins diet was negative 4.7 kilograms, and the 95% confidence interval was negative 6.3 to 3.1, or written with positive numbers, people lost between 3.1 and 6.3 kilograms. That's the 95% confidence interval for the average weight loss on the Atkins diet. The zone diet, that confidence interval, people lost an average of 1.6 kilograms, and the confidence interval there was, well, 0.4 to 2.8. What else we have? Learn. That interval was 1.3 to 3.8. And then Ornish, 0.8 to 3.6. And then also notice that this little bit that they said here about the significantly different between the Atkins and zone is because these two intervals have no overlap. That's why they can conclude that there really is a difference between these groups, whereas the Learn and the Atkins and the Ornish and the Atkins both have a little bit of overlap, although it does seem like it's not very much. So that's a study that you could look at if you feel like it, but it was just an example of how confidence intervals were used in a real-life study.